Hi, now welcome to this video on geometric series. So, like arithmetic, there is a proof. I'm not sure if it was actually done by the same person, Carl Gauss, but more than likely. So, we looked before at the sum of some numbers. So, the first term in arithmetic was A, first term in geometric is A. The only difference being that we're now timesing by a common ratio. So that's the first term, that's the second term, third term, fourth term, and that's going to continue till we get the penultimate, n minus 2, and then the final one, n minus 1. Okay, well, if we were to do this backwards, they don't add up. Like, for example, 1 adds 2, add 3, add 4 that's just arithmetic. That's a stupid example. So let's just do times by 2. If we were to put these backwards, you see that that's a 9, but that's a 6, and there is a pattern, but obviously and it's pretty easy for just 4 terms. But when this gets a huge amount of terms, it's naff. It doesn't work, so it doesn't help us at all. So we have to start thinking about, well, what would help us? And if you think about the arithmetic, things cancelled out and we just had the same pairing each time. So what could we do to cancel some of these out? So what we did, we decided to times it by r. And watch what happens. If we times this first line by r, we get ar, then ar squared, ar cubed, ar to the 4, ar to the n minus 1, and then ar to the n. And you should be able to see that they will cancel, they will cancel, they will cancel if we subtract them. Now that poses another problem. So if we subtract them, it's like, well, what order do we want to subtract them? So if we do top, take away the bottom, what we're going to end up with is a left minus ar to the n. So we could factorize for that, so it would be 1 minus r, and we could also factorize for a here, and we get 1 minus r to the n, which tells us the formula for the sum of a series is a 1 minus r to the n all over 1 minus r. But what happens if we did bottom take top? We'd actually have it this way round. And all of these would cancel. So we'd have ar to the n minus a. Factorize. So r minus 1, ar to the n minus 1. And if we divide throughout by r minus 1, we would get r to the n minus 1 all over r minus 1. Very similar, but the reason we do both, and you're only actually given one, I can't remember which one it is, probably this one on the left, but I will always use this one when r is less than 1, and I would always use this one when r is greater than 1. It just makes it easy. It doesn't matter actually, but it just makes it easier to use. So I'll explain in the next examples which one I would use in which instance. But you do need to know what we've just done off by heart. So learn that, but also learn the proof. Okay, so example 1, find the sum of the first 10. Now we can see here a is 2 and r is 3. So I always start when I'm writing the formula with the denominator. Do I want to do 1 take away 3, or do I want to do 3 take away 1? And my objective is to just keep it looking nice. So I want to do that. So then on the top, if you go back a screen, you can see if it was r minus 1, it was always r to the n minus 1. If it was 1 minus r, it was always 1 minus r to the n. So it's a pretty easy formula to remember. So sum of the first 10, well, that's a, 2, common ratio 3 to to the power of 10 take away 1 all over 3 take away 1, or just 2. They're going to cancel, so all you have to do is work that bit out. And that is 59,048. That seems a massive number, but we've only got 4 terms. Each term is going to be doubling every time, and then we've got to add them. So it's going to get pretty huge pretty quickly. Okay, example 2. So A is 1024. Be careful with the ratio here. We can see it's halving, but also the sign is changing. So that means we're times it by negative a half. And we just want to find the sum of n. Okay. So let's write this formula down first of all. And r is less than 1, so I'm going to set up like this. It's going to give me a nice positive number. If I did it the other way, I get a negative number. It's just ugly. So let's see what we can do. So sum of n, we need to know how many terms there are, which they're not told us, but we can definitely work it out. So we've got 1024, 1 minus r, so that's minus a half to the n, over 1 minus a half, that's 3 over 2. But we need to know what n is, so let's have a little think. So let's work out what the nth term is. So u to the n is a r to the n minus 1. That's from your sequences, geometric sequence video. So when does it equal 1? What term does it equal 1? So that would be 1024 times minus a half to the n minus 1. Okay, so here we're going to run into a slight problem, because you're thinking, yeah, I've got powers, I've got equations, I'm going to do logs. But we have a slight issue with that. If I was to take logs to both sides, I can't log a negative number. So that causes me a problem. But what I do know is this left-hand side is equal to this right-hand side. And anything squared, or anything to the power of 4, or anything to the power of 6, or any even power up here will always be positive. And you can see this left-hand side is positive. So what it tells me, that n minus 1 must be a positive number. So if I think about what does this have to be? Right, what power am I going to raise 2 to get to 1024? I don't have to worry about the negative. And that is 2 to the power of 10. So that must be true. 1 half to the power of 10. I'm just going to check that, so I just did that in my head quick. So to the power of 10. Yeah, super. So that is equal to this left-hand side. Both of these sides are equal. So therefore, I know that n minus 1 must equal 10, and therefore n is 11. Now using that, let's change colour. I can pop all of that into here. So I'm actually going to have 11 terms to get it down to 1. So I'm actually finding the sum of 11. So I've got 1024, 1 minus a half to the 11, all over 3 over 2. I'm just going to type all of that into my calculator, and you should get 683. So the negative numbers really keep the numbers small, but that's it. Okay, that's a tricky question because you can't take logs of a negative. That's pretty hard. Okay, example 3. Let's have a look at another one. So we've got 1 plus 2 plus 4 plus 8. So we can see instantly we've got a equals 1, and we've got a common ratio of 2. How many terms are needed for the sum to exceed 2 million? Okay. So let's just set it equal to 2 million rather than greater than. Just makes our life a bit easier, and we can just think about it at the end. So it says sum, so let's go for the sum formula. Start with the denominator. How's it going to look nice? That way round. So r to the n minus 1. So the sum has got to equal 2 million. Oh, 1 0 short there, I think. 1, 2, 3, 4, 5, 6, yeah. A is 1, it's always nice. Don't have to type it in. R 2 to the power of n minus 1 all over 2 take away 1, which is 1. So let's just get rid of all of those straight away. Add 1 to both sides. And now it's just a simple log problem here. So I'm going to assume you can do that. You could do log of 2,000,001 to the base 2, or you could take logs to both sides and do log 2,000,001 divided by log 2. Either way, what that gives you is 9.967 blah 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 blah. No, it doesn't. It doesn't give you that at all. Just it gives you 20.9 whatever. Yeah, loads of stuff after it. So 20.9th term obviously isn't a term. We can have the 20th term, we can have a 21th term, they're discrete values. But when it's 20.9, it equals 2 million. We're talking about exceeding, so it has to be the 21st term. Okay, yeah, that's definitely enough. So, get practicing, loads more to come, and I'll see you next lesson.